Hey, it's Tony from Adafruit, and in this stream I wanted to share some interesting information about memory optimizations with MicroPython. So I was out at the Hackaday Super Conference over the weekend in Pasadena, California, and I had a neat little demo that I'll show folks. Well, actually here, let me switch to a different view so that we can see it. So on the workbench over here, you can see this is the LED matrix feather wing, and connected to it is the Feather M0 ADA logger. This is a little magnet that I put on the back so that I can actually clip this to a shirt or a jacket and then wear it on here. And you can see it's scrolling a message. So this is pretty cool. It says MicroPython rocks. And this is all MicroPython code, obviously, that that's controlling how this message is scrolled. And let me add maybe my head to the bottom of this shot so you can kind of see me right here. So I wanted to talk about how I built this demo and a really important kind of challenge that I ran into that I think a lot of people are going to have as they deal with MicroPython, which is memory usage. Because when you use Python on like a Raspberry Pi or your home computer, rarely do you have to worry about memory usage because you probably have a gigabyte or more of memory, and so even just fitting lots of data into memory, it's never really a concern. It's pretty rare that you deal with it. Whereas on a little microcontroller like this, so this SAMD21, it only has 32 kilobytes of memory, so that's really small. That's smaller than all the characters in a tweet, probably. Like when you add in like Unicode, definitely smaller than an image of an avatar of a user. So it is not much data, and you can run into problems because this font, for example, that I'm rendering right here, there are a lot of characters and there's a lot of data that makes up that font, and if you're not careful, you might try to put that all in memory and we'll see what happens. You might run into problems, and then it's like, okay, now how do you make this work? So I'll show you a couple of nice tricks to deal with some of these memory issues here, and how I got these LED scrollers to work. And I'll show also real quick, so there are actually two parts to this demo. If I unplug this board, I made a version of this that works with the Charlieplex feather wing. So if I show you, so you can see this is the Feather M0. This is the ADA logger version, which has a little SD card slot. I'm not using it yet, but it could be a fun thing in the future to mess with. But the Charlieplex wing, so I've shown a guide on how to use this, and this wing has a grid of little LED matrices, or little LEDs that makes up a matrix. And if I plug this in, then oops, I got to make sure that I get it in the right header position there. There we go. So if I snap that in like that and plug this in, and then I'm going to run a script real quick from my computer, then we should see a similar message scroll across. So let me just change real fast. I manually kick off how these messages are run. So when I run this, now you can see this is scrolling the same message, MicroPython rocks, but this is a different type of display. So you saw this was the LED matrix above, and then this is the Charlieplex feather wing below. So the Charlieplex actually has one extra row of pixels. So this is 7 pixels tall, whereas this one is, or sorry, the LED matrix has one extra row. So the Charlieplex is 7 pixels tall, the LED matrix is 8 pixels tall, which does make a difference because this font is actually 8 pixels tall. So on the Charlieplex, you can see the Y, the lowercase y in Python has the last row kind of clipped off. But it's still pretty readable and still works well. It's a little hard. There's the exposure on this camera makes it kind of difficult to read, but when you see this in person, like if you look like that, it's really nice. It's bright and it just scrolls across. It makes a nice little message display for this. So let's see what I ran into, some of the issues, or at least how I got this to work. So I'll switch to the main desktop view real fast so we can just look at everything all up. So, okay, so on the desktop here, we'll look at a few things. So first of all, I had to figure out how to render this font because in MicroPython, the graphics libraries are really basic. So if you've seen the tutorials, you can basically put pixels and fill the entire screen, and that's it. So I needed to implement some font rendering. And I went to the Adafruit GFX library, which is our Arduino library for dealing with all these little wings, like the Charlieplex wing, the LED matrix wings, all kinds of things. Use the GFX library, all the little TFT LCDs. And inside of here, we actually have this font defined. So there's this glcd font.c, and this is a really simple font. It's a 5x8 character. It says 5x7. It's technically 5 pixels wide by 8 pixels tall. It's just almost every character does not use the bottom row, except I've noticed like the lowercase y, and I would bet some of the other lowercase ones, like a G, probably uses it. So for the most part, it's 5 by 7, but 5 by 8 technically, if you want to get down to the nitty gritty details. But you can see it's implemented as just this big array of bytes. And so how this thing is laid out, basically for every 5 bytes, this defines a single font character. And it's defined by each column. So each byte defines the 8 pixels in a column. So, if you look at the display and you see that each column going down, that's, on this display it's 7 pixels, but on the other one it's 8 pixels. So each of these columns is a byte inside of here, and then 5 of those columns together makes up a single character. So you can see as this thing scrolls across, like the PYTHON, each of those is a single character, so they are 5 bytes wide. And that's what each of the rows in this file defines. So you can see that this the character position 0 is the null character, which there's no representation of that. But this is laid out by kind of the ASCII characters. So if I look at an ASCII table, then we could look up like the A character, for example. So let's just grab the ASCII table here. So if I look at, let's find an interesting character. So an uppercase A is going to be 65 characters in. And so if I look at the position here, so I'm at line 19, so 20, so around line 85, I should be, let's see, yeah, like line 84. So one of these lines should be like the A character. And basically these are the bytes. So then, think of this as here's the first column, here's the second column, here's the next column. And if I open up the calculator, if I look at the bit values of these, so like let's look at 7C. So if I type in hex 7C, then look at the characters, the bits right here. So you can see like 0, 1, 1, 1, 1, 1, 0, 0. So this is telling me, this is the bits or the pixels that should be flipped on for that column. So just from the top going down, it'd be 0, 1, 1, 1, 1. So, off, on, all the way down, just following the bytes that are defined in that 7C character right here. And then for the next row, or the next column rather, it's the character OX12. So if I look at this in the hex bytes for this, then this is 0, 0, 0, 1, 0, 0, 0, 1, 0. So this is maybe the inside of that A character you can see here. And then if I look at the next one, it's OX11. So if I look at that, then we'll just change this to 11. So you can see this goes down. And actually, I don't think this is the A character that I'm looking at. It's probably a different one. But you get the idea here that each of those bits defines which pixels should be turned on, and that 5 bytes make up an entire character, and each byte is a column of character data. And so that's what this raw font data defines. And it's all just compiled into memory on Arduino. And then the font rendering functions are actually inside of the GFX library C++ class. But all that it does is just pull out the 5 bytes for each character, and then goes through each of those bytes defines a column, and then goes through bit by bit to turn on the pixels. So that's what I started to implement with MicroPython, and I'll show you the code that I did for that. So I call this font bad.py because I'll show you why it's bad in a second. So I just did a very simple implementation where I directly copied this glcd font C file and just converted it into Python. So you can see I made this font variable, and in Python you don't really have a concept of types, you just have numbers. So this is effectively an array, but it's an array that's never going to change. So I made a tuple by just using the parentheses. So this is just a bunch of values that are just a bunch of integer values as far as Python is concerned. And so I just directly copied all that font data. I even kept in all of the comments that are in here. So this kind of shows what some of the characters are. And this font is really nice. It has 255 characters total, so it covers things like umlauts and like some of the extended ASCII characters. So it's a handy little font to have. But you can see this is pretty big. There's a lot of data in here. And then I wrote a little class to just render this font data. And I'll come back to why I have kind of this context manager stuff here, because I'll show you how I actually made this work. But If we look at this, the draw character function is really the meat of this, the thing that matters. And so what this function does is you give it a character, an X and a Y position, and then you can pass it in some extra arguments like the color, which it's going to forward on to the pixel drawing function, because this is kind of cool. I made this to be generic, so when you create an instance of this font render, you give it a function to call whenever it wants to draw a pixel. So this way it can work with any display. So you create this font renderer, and if you're using this CharliePlex display, then you tell it, okay, here's how you draw a pixel on the CharliePlex display. Like in the CharliePlex library, there's a pixel function that you can call. It expects to take an X and a Y parameter as the first two parameters, and then like an intensity or a color value after that. Whereas, I can use this exact same font renderer class with the LED matrix, because I just pass in a different pixel rendering function, and then it'll call the LED matrix pixel rendering function instead of like the CharliePlex rendering function. So that way I don't have to have a font renderer class for each of these displays. I just have one class that's going to call the pixel drawing function that could be used on any display. And so you could use this with NeoPixels, for example. Make a function that just draws on a NeoPixel grid, and you can send it into this font renderer, because it doesn't care how that pixel drawing is implemented. It just needs to know there's a function it can call to draw a pixel at a location. So that was kind of nice, and that it made it a little bit generic, and that's why I can show both those demos and I didn't have to write a bunch of code for it. But anyways, the draw character function is what actually draws the character. So it needs to know the character, the position, and then extra arguments to forward on to that pixel function. So this could be like the color that it passes on. The first thing it does is it just clips out any characters that will be drawn off screen. So, if I try to draw a character like way over here that's never going to be visible, this first little check just looks to see if the character you're trying to draw is outside the visible screen, and then it just stops. It just returns, like nothing's going to happen. Nice little optimization, because, I could waste a bunch of time doing this, but it's going to take time and cycles, and it's just, not going to be efficient to do that. So wherever possible, I try to do less work. And then if I pass this check, so if I know that character is going to be rendered on the display, what I do is I look at the width of my font, which at the top I just defined as a variable here. So 5 pixels across and then 8 pixels tall. I have a height defined up here also. So I look at the width, and I go through each of the pixels in my font. So remember, there are 5 pixels in the font. And then I grab the byte that's associated with all of the columns of data inside that column that I'm looking at, or all of the rows of data inside that column. So, basically I go through each column, that's that character X, and I grab the byte that defines the data for that column. And so by grabbing that byte, I'm just doing an array lookup inside of that font data tuple. So that font data is this giant array up here. So I just index into that. And I do this based on, basically I grab, and actually there's a little bug right here, because I was playing around earlier and I actually recreated this file. So sorry, this is actually how this file should look. But anyways, I look up, so I grab the character that I'm looking at right here, and oops, let me make sure I put a parenthesis back there. So this ordinal character, this gives me back the integer value of that character. So it's just like looking at the ASCII table, and so if I pass in the character A, the ordinal value is going to return back 65. And so that's telling me character A is 65 positions into my font index, or my font data structure that I have. But then I want to multiply that by my font width, because remember, each character is made up of 5 bytes. So the A character is at position 65. That's 65 characters ahead of all the other characters, but each character is 5 bytes wide. So that's why I multiply by the font width, to just make sure I get to really that start of that character position. And then I add in the current column that I'm looking at, because remember, I loop through each of the 5 columns here. So, I mean, ultimately, I'm just pulling out which byte do I care about. So if I'm looking at a character, I start with the first byte, I go through all the bits inside of it, I move on to the next byte, and then the next one, and the next one, until I get through all 5 bytes for that character. And then once I have the byte for the character, for the column of data that I'm rendering, then it's just a matter of going through all 8 of the rows inside of that column and just drawing them if there's a bit set. And so that's what this does. This will just shift over this byte that I read the number of times based on which row I'm looking at. So it starts at 0, so it's looking at the very top bit, and then the next bit, and the next bit, and the next bit, or not the very top bit, but I guess the very last bit, and then the next bit, next bit, next bit. So it's just going through all those bits. and looking to see if they're set. So if, basically if it's and the value 1, so if the low bit is high, this is going to be true down here. So if that's the case, then I draw a pixel. So I call that pixel function that was passed in earlier, and I give it the x position offset by the current character x position, the y position offset by the current y position of the character, and then I just pass in whatever color arguments were passed into this draw character function. So this way, like if you're drawing on a NeoPixel display that takes in like a tuple of red, green, blue values, it's going to silently pass this through. And you might not have seen this syntax before, but basically this is the syntax in Python to say that a function can take in any number of positional arguments and any number of keyword arguments, and then you can pass these along to another function that you're dealing with. So that's the pixel function. I'm just going to basically say, any extra arguments that were passed in here, just forward them along to pixel. Don't even worry about what they are. Just send them along to the pixel function here. So that's how this function works. Again, it works. It just goes through, figures out which character you're rendering, finds which of the 5 bytes to render for that character, and then just goes through column by column, and then for each column, row by row, to set each pixel for that character. And that's basically all that it's doing. Then I have a little text function here that you can just pass in a string of text instead of a character, and then all that it does is goes through each of the characters in that string of text and then calls draw character and just moves along the line, and it actually adds an extra line of blank pixels in between each character. So that's just so that each character is not immediately next to the character. So you can see like the M, or between each of these characters there's a line of blank pixels, and so that's that little extra 1 offset that I'm doing here. And then I also have a function here that just gives me the width of a text string in pixels. So that's just helping me to know, in my main scrolling logic, which I'll look at in a second here, I need to know how wide is my message, so that once it scrolls off the screen, I swap back to the beginning. So I need to know how many pixels long this MicroPython rocks text message is. So that's how my font rendering works, and we'll come back to why this is bad in just a second here. Let's look at the code that's actually scrolling this message across. It's this charlieplex scroll.py here, and you can see I tried to make this a little bit generic so that I have some variables I can change here. So like if I want, this is running on the SAMD21 board, so I'll change this to SAMD21 MicroPython rocks. And then if I run this again here, you'll see, okay, now the message updates. And then I can also tweak the speed at which this scrolls. So if I want to make this scroll a little faster, so this is like the speed in pixels per second, if we double it, and then if I run this again, we'll see that, oh, it's a lot faster. So it's kind of scrolling by at a higher rate there. So kind of nice, easy to tweak the values of this. Oh, and this intensity kind of controls the intensity of the pixels. So if I crank this up to 255, then the pixels should get a lot brighter. So we'll slow it down, and yeah, you can see like, whoa, that's much brighter text there. So that's kind of the basics of how this works as far as like what variables you can tweak. And then as far as the code goes, so I have a main function. This is a kind of a convention that I follow a lot that takes in an instance of the I2C interface. Down at the bottom, this is actually the very first code that runs. It uses the context manager, which I've talked about, and look, if you look at the charlieplex guide, it talks about why you might want to use this on the SAMD21 port, and it just calls that main function and passes in an instance of the I2C bus. So nothing fancy here. I've done this in a bunch of videos. And then inside the main function, I just create an instance of the Charlie Wing matrix class. And again, look at the Charlie Wing guide. This talks about how to use this. I clear the display. And then I use the font renderer class, which we saw in this font band.py. And I'm using it as a context manager. And I'll explain more why in a moment why I'm doing this. But I'm using this as a context manager, so I get an instance of this font render, and you can see I need to pass it in my display width, my display height, and then the function to call to draw a pixel. And so the function that it's going to call to draw a pixel is the matrix, the charlieplex matrix.pixel function. And so that function takes an x position, a y position, and then an intensity, like the value that it should set that LED to be. So this is kind of cool. This is why this is so generic. I'm just telling it, use the charlieplex matrix pixel drawing function here. Then I keep a little bit of state here. I won't go too far into this, but basically I keep track of what's the current position of the message. This is just like on the SSD 1306 little text scroller video that I did. I keep track of the message. I'm not moving it in a sine wave in this case. And then I need to know what's the width of my message. So I use the width function on this font render class that I was just mentioning. And then for the Charlieplex display, I actually do frame double buffering. So, when it's drawing the next frame of animation, it draws it on an unseen buffer, because remember the Charlieplex display has 8 buffers, so you can draw on one buffer while you're displaying the previous buffer, and then I just swap over to the new buffer so that you don't actually see all of the pixels changing. I tried it without doing the double buffering, but you notice the screen will blank and then all of the pixels will be painted on, and you get some flickering because of that. So I basically just swap between 2 different frames where I'm showing the old frame and drawing on the new frame, and then I swap the frames so that now my new frame is my old frame, and then I start drawing a new frame on what was the old frame there. So I'm just swapping between those 2 buffers here. And then I have to keep track of the current ticks, because I want to know how much time has elapsed between each loop iteration, because I'm moving this thing at a constant speed. And so I need to figure out, in this little block here, how much time elapsed since the last time this main loop ran. And that time is just the number of ticks in milliseconds. And then I can figure out, okay, what's my position by just multiplying the elapsed time by my speed, which I compute as my speed, the number of pixels that should scroll, number of pixels per millisecond. So I take my speed, which I normally define in pixels per second, because that's easier for me as a human to kind of understand, like, okay, 25 pixels per second, that seems pretty fast. Whereas my time ticks are in milliseconds, so I just need to divide it by 1,000 to get my speed in pixels per millisecond. So, I could actually say, instead of 25 pixels per second, this is 2,500 pixels per millisecond. Or sorry, this is 0.0025 pixels per second, but it's hard for me to understand that as a person. So I like to put this in units that I can understand. And it doesn't hurt, because I'm only going to do this once during the initialization, so I just convert this into my speed in milliseconds. But then it makes it really easy. So for my position, I just multiply my speed times the elapsed time, and I just offset my position by that amount right here. So I subtract that so that it moves to the left effectively. And then I look to see if my position scrolls all the way off, so far off the screen that the message is not visible anymore. I just reset to say, okay, move the message back to the far end of the display right here, the width of the display, so that it starts scrolling from the end there again. And so that's what this little check does right here. Then I do this frame swapping thing where I'm just constantly swapping between, the previous frame and the next active frame, so that I'm not drawing on the visible frame, I'm drawing on the invisible frame right here. And then I draw my text message here. So I clear out the matrix with this line above. I draw my line of text at the current position, which, remember, that position moves based on the velocity here. And you can see I'm calling that text function. I'm giving it the message, which is just defined as some static thing up here. And then I'm giving it the X position, which is that position variable that's always going to scroll across. The Y position, I'm just always fixed at the very top of the screen, because I know, this font is only, it's large enough that it's going to fill the entire screen for both of these to display. So I'm not really going to be moving it up and down. So it's always going to be at the Y position 0. And then the intensity value. So this is one of these magic extra parameters where if I go back to this text function, it only takes in text X and Y, but you can see the way I call it here, here's text X and Y, and then an extra parameter. And so that's where the magic of this args and KWArgs, or keyword arguments, comes in. So these suck up this extra argument and just forward it along to that draw character function. And so that's how, ultimately this intensity is going to be passed on to my matrix.pixel function, which the font renderer knows is the function it should call to draw each pixel, but it's going to pass along this intensity value that it sees there. And so that's how the intensity stuff works. And then I just sleep for a little bit of time, because kind of right now on the SAMD21 port, you need to sleep to make sure that the mass storage device works. And it's something that we'll deal with later. But in general, it's usually good to sleep a little bit and give some extra time here, because unfortunately there are some allocations. So the garbage collector is actually running right now. If I connect to this in the serial port, which I can actually do if you want, we can see. So if I connect to the serial REPL, you'll see, this is the debug output. So my garbage collector is running. This means that something inside of my main loop here is allocating memory. And there are some things like the pixel functions in the matrix class are not super optimized. They're allocating memory. So In the future, we're going to try and get rid of this, but for now, you can see the garbage collector is running. Interesting, though, that it doesn't really seem to affect the speed of this that much. It seems to run just fine, but I'll close the serial REPL here. Okay, so, you see this thing working, but let's actually try. So if you look closely at this code, I'm not actually using fontbad.py. I'll show you on my Python board here. So this is the file system on here. I do have fontbad. I actually have it as a .mpy file, because if you look at fontbad.py, this is actually 10 kilobytes of text data right here. So all of the text for this file is 10 kilobytes. This is a lot of data. So I actually have problems copying this file to my board, because I need not only my fontbad.py file, I also need my my HTK, the driver code for the LED matrix, and I also need the driver code for the CharliePlex thing. That's the IS31FL3731. So I need these MPY files that drive my displays, obviously, and then I need my font files. But I ran into problems because this, just as a pure .py file, this thing was way too big, 10 kilobytes of data. It's hard to fit all that on the file system. And then if I try to import that, even worse things happen, because now all of my memory gets used up. And so actually, let me show you the memory usage here. So I can actually import this font file. So like I was saying, I have the font bad as a .mpy file. I've talked about this before. This is what I called an external frozen module. Basically, you can run a tool, and I show how to do this in a guide, and I'll put links to these guides in the description below when this goes up on YouTube, so you can look at some of these older guides that talk about how to generate this .mpy file. But basically, the mpy file is just, by running a tool against this fontbad.py file, it gives you a smaller file that takes the source code for this and converts it into the Python bytecode that MicroPython will interpret. And so this .mpy file is actually a lot smaller. So you can see the .mpy file is only 4 kilobytes. So it's not 10 kilobytes. So it is noticeably smaller. And it does actually fit on the board. But let's see something interesting. So I'm going to connect back to the serial REPL, and I'm actually going to just Control-C, stop the script. I'm going to Control-D to just reset my board, so I make sure there's nothing kind of running. You can see it just froze here because it's the display is not running anymore, it's just showing the last thing that it had there. But let's look at an interesting function. So let's import the MicroPython module, and let's call micropython.mem_info. Oops, not info, info. So this function gives you a little bit of information about the memory usage. So the important thing here, so there's this stack usage, which I'm not actually sure what this thing is showing. Maybe I'll look more into this later and we'll figure it out. But the GC line here is kind of showing your MicroPython memory usage. And so it's showing you that basically you have about 16 kilobytes, 15,936 bytes available. That's memory that's on the heap. So that's memory for all of your variables and all of your stuff, and even your MicroPython scripts. Anything that has to take that heap memory is going to pull from this pool of about 16K. That's all you have right here. It's telling me that I have 832 bytes that are used. And remember, I reset my board, so there's nothing that's loaded, there's nothing that's running. My main.py is empty. My boot.py just does the bare basic stuff. So, just a default kind of state. I'm using 832 bytes. And then I have about, almost 15K of bytes available to me. So let's import this fontbad.mpy and see how my memory usage changes. So import font_bad. And okay, so everything's okay. And now let's call that meminfo again. And whoa, uh-oh. So again, my total available memory doesn't change. This is fixed. But now I'm using about 10K of memory, and I only have about 5K free at this point. So I just went from 832 bytes to about 10 kilobytes just from importing this data. And that makes sense because, if you remember, the raw source code was about 10K of data. So it's interesting that, I'm roughly using about 10K of that data on my heap here. Okay, so you might still be thinking like, well, we still have 5K, sure, maybe we can make something work. So let's try it. Let's actually change this CharliePlex scrolling function. Let's import font bad as font. So I'm just going to import this font bad module, but I'm going to rename it so that it's called font. And that's just because my code is written to use a module called font. And so this is going to import font bad, but call it font so that I don't need to change my code below here, so that this with font.font renderer, this is going to work. It's just going to use font bad as the code for this. So let's exit out of here. And actually, I'm just going to Control D, just going to reset the board, and then I'm going to exit out of here. And now let's run the charlie scroll.py. And uh-oh, something's not happening here. Oh, I'm sorry, actually, so I'm running this with the -n option in Ampy. That just says run the script and don't grab the output. Let's run the script and let's grab the output, because obviously it's not working. It's not scrolling. So when I run this, uh-oh, I get an error here. So Ampy just tried to run this script, but while it was running the script, it failed. And it actually failed with this memory error. Memory allocation failed, allocating 5,000 bytes. And this is at, let's see, it's in fontbad.py at line 262. So if I go into this, and if I scroll all the way down to 262, so it was, so it's basically in the creation of this font render. So it's interesting. It must have been when it was trying to import this font rendering module. So, you know, probably got through to like this line right here, and it's probably trying to allocate memory for this class. But it couldn't do it. Uh-oh, you know, it ran out of memory here. So, you know, it wanted to allocate a chunk of like 5,128 bytes. But if you remember, after I imported font bad, so if I go back into, you know, the board here, and if I reset it, let me go back to, let's get out of the raw REPL, and then let's, no, come on, let me exit out of here. Let's just unplug the board and plug it back in, because I want to show, you remember, it was trying to allocate 5,128 bytes. Remember that number. And then if I connect back to here, if I, well, let's import MicroPython, and then import font bad. And if I call MicroPython dot font, mem info, now we see, oh, interesting, wow. There's actually more memory available this time. That is very bizarre why I did a hard reset and there's more memory. But oh, anyways though, so I guess I didn't really make the point that I wanted to right there, but obviously this doesn't work. So, you know, it doesn't have enough memory to load all of this font data, even as a .mpy file. You know, it can't load all this font data and the code to render it, and the code that I'm trying to run right here. Because remember, this code is importing other stuff. This is importing that IS31 CharliePlex module, and so that's going to take some memory. It's importing some other modules that are being used here. That's going to take some memory. There's some state inside of here, like these variables. That takes memory. You know, all of this stuff is taking memory, and there's not enough, unfortunately. So at this point, you know, what do? I tried the .mpy file module. You know, that didn't really help because the data itself, that helped me to get the file onto the board. You know, it's a smaller size, but importing it, now everything explodes. So I actually stepped back and thought of an interesting way to solve this. Earlier today, actually, talking to Scott, we had a good idea. You know, one way that I solved this was I can actually freeze this module into the MicroPython firmware. Even that takes a lot of memory. It does work, but a better way to do this is actually, you know, because I'm looking up each of these characters, when I'm rendering a character, I just need to know the 5 bytes that make it up. I realized that I don't have to keep this entire font data structure in memory. I mean, maybe it would be nice to keep it really fast so that I can look up those 5 bytes really quickly, but I could actually store this in a separate file and then just read that file and seek to the position that I care about. So if I put all of this raw data into a file, you know, all the data that makes up this font character, I could open that file, and you know, in MicroPython, you can use the open command. You can open a file just like in normal Python. You can seek to a certain position, because that's all that this font renderer code is doing. You know, it's just going down and it's just indexing into that font data array, which is like if you had a file, you can just seek to a position that you know of inside of that file. And then I seek to that position and I grab the 5 bytes that I care about and then use that to render the character. So that's actually what I did. I made a new version of this font render, which is font.py. So this is the good version. This is the version that you want to use. And the way this works is it will actually read another file that I loaded onto the board, this .bin file, which is just the raw bytes of that font character. but now I can actually seek into that character. And so if you look back at the board, I had a few other files on here that I didn't mention before. So I have this font 5x8.bin file, and then my font.py file, which is the code we're going to look at here. Now this bin file, basically the way I generated this was I just made a little Python script that just takes my font data again, and this I ran on my computer. I didn't need to run this in MicroPython because I'm just running this ahead of time to generate the .bin file. So I have my font data again, and then just some real simple Python code right here that just will open a file for output, writing bytes to it. And I will just write out, so the first 2 bytes of the file, I write out the character width and then the character size. So that's just nice in that, I'm maybe making a font file format of sorts for this, so that that way I don't have to hard code into my font render that it only works with 5x8 pixel fonts. This way I could have like maybe 7 byte long fonts, 7 characters wide or 8 characters wide. I could change this, but I'd have to make sure that I change all this data obviously to match that. But so the first byte is the width in pixels of each character. The second byte is the height in pixels of each character, so that's 8 pixels. And one little caveat is that this font renderer can only handle up to 8 character or 8 pixel tall fonts. If you go larger than that, it's not smart enough to know that it needs actually to find extra bytes for each extra kind of column, because a column can only have up to 8 pixels because it's a byte wide. But anyway, so I write out those 2 bytes, and then I just blast out. I go through each of the bytes in this font data structure and just write them out one by one in order to this file. And so that's how I generated this font 5x8 bin file. And you can actually see this file is really small. It's only 1 kilobyte in size. And that's because, I'm not storing the actual characters that make up this font. I'm actually just storing the byte for each font. So it's real small. And it's nice that I save more space that way for this. So, okay, so I have this little 5x8.bin file. Let's see how my font.py renderer changes. And so one big change is that now that I'm opening a file, I need to make sure I close it. And so that's why I have this init and deinit function. So, I kind of follow the convention for a lot of things in Python and MicroPython where, this font render has a resource that it needs to handle, which is basically a font file, this font 5x8.bin file. And so you need to, after you create a font render, you have to call init, and then it's actually going to open that file right here, and it's opening it for reading, and then it actually will read what's the width and the height. And unfortunately in Python, when you use the read function, so you can see right here, I'm calling on this font file. So like this line right here will open the font file. This line will read 2 bytes from the font file. And then it uses the struct unpack function to pull out 2 bytes. And then it just saves the first byte, like the integer value of that byte, in the font width variable that's saved on this class. And then the second value is saved in the font height right here. And unfortunately, like, you can't just directly take the bytes that you read, because in Python 3, the read function returns back a byte string, but you can't convert a byte string into an integer because it needs to know how to decode that in some way. So you have to tell it, like this uppercase B. If you look at the struct unpack function, the uppercase B says this is a single byte unsigned character, so a value from 0 to 255. So, but I mean, ultimately all that I'm doing here is I'm reading those first 2 characters that tell me the width and the height that I saved ahead of time, and I'm just storing those as variables on this class member here. And then the deinit, this just closes the file, so I just make sure that I close the file. And then this enter and exit, these are context managers in Python, and so this is what allows me to do this with font renderer, created as a context manager, so that when all of this main loop code is finished for any reason, then it will actually make sure that that deinit function is called, because it's going to call this exit function, and then that's going to call deinit, and deinit is going to make sure my file is closed. So it's just best practice here. I mean, I don't really technically have to do this if this script is just the main.py that's always running, but it's nice to get into the habit of doing something like this. Okay, so now let's look and see how did my character drawing change. And it really didn't change much at all. I'm just referencing now my font width and height because I'm storing those on the class, as class members instead of just like global variables. I'm just using them here, but this logic is exactly the same as the bad font render that we saw before. Really, the only change is right here in how I look up which character to find. So remember, in the bad font render, I just index directly into this font data structure because it's in memory, and I know, I just need to index into it and I'll get the value. Whereas now I need to seek inside of this file. And so I seek with an offset of 2 because I need to skip those first 2 bytes that store my width and my height, my pixel height. Skip those bytes, and then I just offset exactly the same amount that I was offsetting before in my bad font render. So I take the ordinal value of the character, multiply it by the number of bytes in each character, like the number of columns in each character, and then offset that by the current column that I'm looking at. So that will seek to that position in the file. And then the next line is I actually read that byte. And so I call the read function and I read 1 byte right here. That's what that 1 parameter says. And then I have to unfortunately use this struct unpack to convert that byte string value into an actual integer value here. This is a little ugly. I wish there was a better way to do this. Maybe there is a better way, but this is the only way that I kind of saw it work, because unfortunately this is allocating right here. You can't really tell, but it's actually creating a tuple, and so this is going to cause the garbage collector to run. So in the future, hopefully I'll find ways to get rid of this allocation, but it does work. It seems to be fine. But that's the only change, and the rest of this logic exactly the same as before. I'm just going through each of the rows inside of that byte of data that I pulled out, and I just test to see, I iterate through each pixel and just look, is that pixel set? If it is, call that pixel set function, and everything is the same. Like my text drawing and my width functions exactly the same as before. So this is nice in that my code is really similar, but now it's reading from this font 5x8 bin file. And so let's see how the memory usage changes when I import this font render, or this font.py class. So let's go back to our board right here, and I'll make sure it's not running anything, and I'll just give it a quick little reboot to make sure that there's nothing running. Now if I import MicroPython, and let's call micropython.mem_info. So okay, so now we see, yeah, we've used about 624 bytes. Now let's import, instead of importing font_bad, I'm going to import font. And so font, this is the good one. This is the one that uses that extra file. So I do that, and now when I run meminfo, hey, look at this. Now instead of using 10 kilobytes of memory, I'm only using about 2 kilobytes of memory, and I still have 13 kilobytes free. And that is the crucial difference why this code now works, why my CharliePlex scroller works. So if I change this back to just import my good font renderer, and if I save this, if I exit out of this right here, and if I kick off running that with the Appy tool, now we can see it's working. And that's because, it's only using about 2 kilobytes of memory to do this font rendering, whereas before, when it was trying to load all of that font data into memory, it was using 10 kilobytes before it even got a chance to load the rest of my script. So, the rest of my script obviously must take more than 5 kilobytes of memory because that allocation was failing that we saw before there. So that's kind of the whole point of this stream. I just wanted to go through and show some of the tricks and things that I ran into while making this demo. And, eventually I'll probably do a separate guide on this font render. Like this font render, I actually want to turn it into a little library that we'll have, because the cool thing is, because this is an external file, I could have other fonts that I define. And as long as those fonts are just, 8 pixels tall, they can be any number of pixels wide, you're just gonna have a larger file. I could have different styles of fonts inside of here, which would be kind of cool. So like you could customize this. I mean, there's no real tool that I know of. You're going to have to like build those bytes by hand or find some tool to convert a bitmap font into that format. But this is cool. It gives you a lot of flexibility in that, you can just put extra font.bin files on your board. And the way this font renderer works is there's an optional parameter, this font name. So I could reference a different font file and load it. Right now, I'm not specifying that font name parameter here, so it's using the default 5x8 font, but I could have other fonts in here and load them and have like multiple font renders, one that has a fancy font, one that has a simple font, and use those. So it's kind of nice, and I kill 2 birds with 1 stone. I have less memory usage and I have more flexibility. I can load up fonts and use different fonts like that. Whereas before, like if I tried to freeze this into a, if I took this bad font renderer and tried to freeze it into the MicroPython firmware, if I wanted to change the font, I suddenly have to recompile the MicroPython firmware, which that's not really fun just to change the font. So I think that this renderer using files gives me a little bit more flexibility. Now, it's not perfect. Like, this does take a little bit more time. Like, this seeking to this position in this file, you know, it's going to have to go read that from flash memory. So that's probably an order of magnitude slower than reading it from RAM. Like, you know, RAM is really fast. It's super quick for the processor to read from RAM, whereas flash memory, it's got to go out and grab it from, you know, some other part of the chip. And I mean, even in the future, like if you have an SD card, maybe you could put fonts on that SD card, and that's going to be even slower because you're going to have to go over a SPI connection and read from that SD card, or like an external flash or something like that. But ultimately, I don't think it really matters because it's still fast enough. I mean, you can see this scroller, even though every time it renders a character on this display, it's going to that file and it's reading 5 bytes from that file. It's still pretty fast. Like it's still happening quick enough that, you know, I'm scrolling this thing reasonably quick across here, and you don't really notice any impact for that speed, for that hit of having to read from that file. So I think in this case that trade-off makes sense. You know, I don't care about like nanosecond performance here. You know, if it takes a few milliseconds or whatever to grab the data, that's fine. You know, I'm not really scrolling at that crazy of a speed right here. So that's basically what I wanted to show in this stream then. And I do have the code for this in a gist that I put on GitHub. And actually, let's make that bug fix in font bad that I just made earlier before. Let me just scroll up to, where did I have font bad? Oh, did I not put it in here? Oh, I don't even have font bad in here. So, okay, so we don't need to make that bug fix, so I don't have it in here yet. In this gist, I basically have the Charlieplex scrolling code. That's the good one that's running right now on here. So this is just showing, you know, this is, if you want to do a text scroller, this is a cool little example of it that I'm showing here. I have the font.py. This is the good font renderer that uses that file, so you can grab this out of here. I also have the font5x8.bin file, so that's that extra little file that I copied to the board before that I generated ahead of time, so you can just grab that from the gist here. You'll probably have to view the raw and maybe save it, or you know, I think if you click view raw, it should download it. Yeah, there you go. So it just downloads it like that. Because you can't open this thing in a text editor. It is raw bytes. It's going to look like garbage. And don't open it in a text editor and then save it, because it's probably going to mangle it. So, you know, you really want to deal with this as a raw binary file. And then I also put in the font2bin.py. So this was the script that I created that I ran on my desktop computer that converted that font data into this .bin file. So just handy to have as an example of how to do that conversion if you want to do it yourself. And again, this is all just based on the GFX library and the font that it includes there. And then I also have the LED matrix scroller code in here. And so that, you know, I'll show you again. If I pull this Charlieplex matrix wing off and then stick the little LED matrix wing on top of it like that, and just snap these in, there we go, and then plug this in. And now if I run the code for the LED matrix scroller, so if I say LED matrix scroller, then there we go, we're scrolling across the LED matrix. And you can see the Charlieplex and the LED matrix scroller code are very similar. Oop, my camera is not focusing super well. Come on there, focus, focus. If we move it around, I guess it doesn't seem to like the, there we go, it's there. Finally, there we get the focus. But if you look at both of the scroller code, they're very similar. You know, it's really, they just change, they differ in how they initialize that matrix. You know, one of them uses the LED matrix class, the other one uses the Charlie Wing class. The LED matrix code actually, I'll show you maybe in the text editor here. It's a little bit bigger. This one I did have to tweak a little bit. So, you know, remember when I create that font render, I pass in a function that tells it how to render each pixel. Now for the LED matrix display, it just so happens the origin for where it renders pixels is at a different location. If I remember correctly, instead of being up here in the upper left, it's down here in the lower left. And so because I wanted the same code to work across the Charlieplex wing and the LED matrix wing, I wanted that origin to be in the same position so that, you know, I could pull one wing off, put the other wing on, and if I had this like clipped onto my shirt, I didn't have to like flip the whole thing over to make it work. But it's really easy because, you know, since I'm passing in a function, I just made a little kind of modifier function here, my own little matrix pixel function that calls the matrix.pixel function on my LED matrix. but I swap my y, I flip my y value, so I invert it, so that now instead of the origin being down here, the origin for the y-axis flips up to the top into the upper left where I want it. And so that makes it nice and simple for me. And that, you know, I can make a little function that changes my origin. I don't have to go in and like change all of the logic of this font rendering to like try and figure out a new position. I just have a little transformation function here. And again, because my font renderer just needs to call a function to make this work, it's cool. I can pass in this little transformer function instead of calling, you know, the raw matrix.pixel function here. So it worked out well. It gives me more flexibility. My cat, you might hear her in the background. She's very excited for some reason about the LED matrix font rendering. So anyways, though, I think she wants to play, so I might want to wrap up the stream in a second here. But again, the rest of this code, pretty much the same as the Charlieplex matrix. Now, one thing I'd like to do, and I'm still working on this, I can't get them, you know, unfortunately, you know, this is still not perfect. Like you saw, you know, the font rendering takes up about 2 kilobytes of memory. The rest of my script seems to take up about 5 or 6 kilobytes of memory. What I would love to do is be able to have one script, one code base that lets me actually just pull out, you know, I can just pop off this LED matrix wing and then pop on the Charlieplex matrix wing. And in MicroPython, it can actually detect when an I2C device doesn't exist anymore. It'll throw an exception, an OS error, and it says like an I2C bus error. Oh, here comes my cat. She's gonna investigate what's going on over here. And she's more put her tail right in front of my face right here. But anyways, so I could actually detect in my MicroPython script when this wing is pulled off, because it's going to throw an exception, and I could catch that exception in MicroPython. And then remember, there's an I2C scan function, so I could go into a state where I say, hey, my wing was just removed, start scanning to see are any feather wings attached to the board, and it could detect when the Charlieplex wing is attached, because the driver on the Charlieplex board, the chip on there, has a unique I2C address that's different from the LED matrix. And so I think that would be a really cool demo where just based on scanning the I2C bus to see which device is attached, it will change which code that it uses to scroll the message. So when it detects the Charlieplex wing is attached, it will use the Charlieplex scrolling code. And when it detects the LED matrix is attached, it'll use the LED matrix scrolling code. And I started to do that, and even with all these memory optimizations, I still am running into memory allocation errors, because I'll actually show you, this is some of the code that I started to write for this. You know, I have a concept of a separate class for my Charlie Wing scroller, and then my LED matrix scroller right here. And then in my main script, I try to detect, so you can see like when I find an OS error is thrown, I try to go into this mode where I'm calling the I2C scan, and then I change my mode when I find a new device. But I was noticing like it can't even run this full script. And it was actually right as I added this print statement to try to get some debug stuff, I started to run into memory limits. So like I am right at the limit of how much stuff I can do. And again, unfortunately, you know, in this thing, like I have to import both of my modules here, my LED matrix scrolling, my LED matrix module, and my Charlieplex matrix module, because this code, it might use both of those. You know, it doesn't know which one it's going to use. So, you know, this is going to take a lot of memory. Like I have to use both of these scripts. So, you know, it's maybe not perfect. Like there are limits. Again, you know, there's only 32K of memory, and you've only got 16K of that for the heap. So there's not a lot of memory available to you. And so it might just be that I can really only deal with one board at a time, you know, one peripheral at a time, which I think that's okay. I mean, you know, that just means that I have to use one thing at a time on this. And if I wanted to get fancier, you know, maybe I should look at a chip that has more capabilities and more power, more memory in particular. And then maybe I could do kind of this multi-scroller kind of demo. But I still think this is really cool. You know, like I showed, this is a good way to do a little LED matrix scroller demo. Again, the code, it's in a gist file here. If you really want to look at it, you can see how to use this code. But really the point of the stream was to just look at what happens when you start trying to do more complex stuff with MicroPython, and what happens when you run into these memory allocation errors. Like, first of all, like, what is the memory allocation error? So like, as you saw, if you get back an error, memory allocation failed, you've probably got too much stuff loaded. And so then you really need to think about, how do I optimize my code so that I'm not loading things into memory? And in this case, I optimized it by saying, well, my font doesn't have to be in memory. I can throw it in a file, and then I'll just seek to the position in that file that I care about. Now, you might not be able to do that in every case. In some cases, you really might need to have a lot of data in memory. Like if you have a frame buffer of pixel data, for example, that you're maybe modifying in dynamic ways or whatever, maybe you could go and save that to a file and then read it back, but try it. Maybe the performance is good, maybe the performance is bad. If you're only doing this like once a second, then that might be good enough. You could save your data to a file, go do some processing, then when you need to use that data, load it back from the file, do what you need to do with that data, and then save it back to the file when you're done. Lots of options, and that's kind of maybe the fun of MicroPython, that you are dealing with a low memory, memory constrained environment. So the things that you might do in a Raspberry Pi or your home computer, just looking at like this array of font data, a Raspberry Pi would laugh at this. It has a gigabyte of memory, so 10K of data, nothing for that. Even an old 486, those old computers, 640K of memory, you could still load 10K of font data there. But 32K of memory, you're running into a little bit more trouble there. So, okay, so I'll wrap up this stream. If folks have questions, maybe throw them into the chat, and we'll see if we can get to them. I'll switch back to the main kind of headshot view here. So we'll go back here and see. Okay, so let me scroll back up. There's a little bit of discussion here. Let's see. Let's see. So someone was wondering, was the Charlie Plex stuttering due to the garbage collector? No, it wasn't stuttering due to the garbage collector. I'm not exactly sure why it's not super smooth, but basically in the code you saw, so I'm looking at the number of ticks that elapse between each main loop cycle, and then I use that to compute the velocity, the new position based on the velocity. But what I think is happening, and then I have this little like 20 microsecond delay or 20 millisecond delay between each loop iteration. And so I think, maybe if the garbage collector is kicking in, it might take a little bit extra time. And so you might see, it's probably jumping between like one extra pixel because it just has to round down. There's no half pixel position. So we're probably seeing in some cases it jumps to the next pixel faster than it might have jumped before because the previous iteration took a little bit longer. So I guess maybe the garbage collector is causing it to stutter, but it's not stuttering nearly as bad as if you didn't use the ticks to figure out, if I just had with every loop iteration a fixed delay, like a fixed period of time that I was waiting, and then I would move some number of pixels, then you really notice when the garbage collector kicks in because it takes more time, and so you're moving the same number of pixels, but it takes longer per frame to do that. And so I'm at least trying to figure out how much time elapsed during the frame so that even if the garbage collector kicks in and takes a lot of extra time, it's going to correct for that, and the velocity and the position are going to move it accordingly for that. But okay, so let's see. Looks like some talk about MicroPython, SamD21. So, okay, cool. I don't see a lot of other questions for this. So I think we'll wrap up this stream then. So thanks a lot for watching. Check out youtube.com/Adafruit. You can see this video, all kinds of other fun videos, and I'll put links to the gist file that has like the font rendering and all this stuff right there. But like I said, I'm going to eventually do a guide and tutorial on this because this hopefully can just be its own standalone library, a nice little font render. Like I said, this could work with NeoPixels, like a big NeoPixel grid. That could be kind of fun. You could have extra font files, so lots of cool stuff planned for that. But for now, this was really just all about how to investigate and troubleshoot memory usage problems. But anyways, check out YouTube to see all the project videos. Check out twitch.tv/Adafruit. That's where I stream these things live. I'd like to do a stream on Tuesdays and on Fridays. So on this Friday, I'm not sure exactly what I'm going to do, but it'll probably be a guide on some kind of MicroPython hardware. So we'll come back and see maybe if there's some feather wings and things that are left, or maybe the font render. Maybe I'll pull that out into a library and we'll do a formal kind of guide and stream on it for that. But until then, click the like, the comment, the subscribe, give us some feedback, let us know that this is good content, and we'll keep cranking out stuff like this. And if you like this stuff, if you like this more advanced kind of dive into MicroPython stuff, let me know in the comments, because I think this is kind of an area that we could do a little bit more kind of videos and streams on to show how you can maybe develop libraries and things for MicroPython, because the previous videos are kind of just showing you how to use these things. So I think it would be interesting to look at, okay, how do we make some of these libraries? So let me know if that sounds interesting, and we'll start to maybe look at more advanced content like that. So until next time, this is Tony from Adafruit. So thanks for watching. See you guys later.